In this video, we'll be looking at Chapter 15, Section D on vector subtraction. Now we have to go all the way back to arithmetic to remember what subtraction actually is. The expression a minus b is really a plus the negative of b, right? And that's what subtraction is. It's the negative or the addition of something's negative. Well, in vectors, it's no different. I can literally just put my vector symbol above these letters, and now I have an expression for vector subtraction. Graphically, what this looks like is very similar to vector addition. If I have vector A and I have vector B, well, I know how to add vector A and vector B. I take B and I place it at the tip of vector A. But remember, I'm adding the negative of vector B, and we learned in a previous video what that is. It's a vector of the same length, same magnitude, but exactly opposite direction. So instead of placing vector B at the tip of vector A, I'm going to place its negative. And so I can draw vector A here, draw the negative of vector B here, and then it's very much like addition. I draw my resultant vector from the tail of vector A to the tip of vector B, and I have the expression A minus B. And these guys should have arrows over them as well. And that's vector subtraction. It's that easy. So let's take a look at a few examples. Here I have a couple of expressions that involve the subtraction of vectors. In the first example, I have vector QR minus SR. Now again, this is a lot like addition, or it's exactly addition, except I'm adding the negative of what's being subtracted. So here I have QR plus the negative of vector SR. But the negative of vector SR is the vector RS. Right? And I can represent that visually here. If this is the vector SR, then the negative has to be vector RS. And once I know that, now it's a straight addition problem, and I have vector QR plus vector RS. And here's a little trick that we didn't see in the last video. Notice how the R's are right next to each other. Right? That means the R's are sort of going to go away. Now this isn't mathematically appropriate, but we can think about the R's kind of canceling each other out. And I'm being left with the two letters that are on the outside here. So I really have vector QS as my answer. So let's try that one more time. With the next expression, we have vector QR minus vector SR minus vector PS. And I know what the first two are already, because this is really I'm really going to add vector RS here. And by the same methods, instead of subtracting vector PS, I can really add vector SP. I'm adding the negative of vector PS here. And notice how I have R and R here. They're going to sort of cancel out, and letter S and letter S here, they're sort of going to cancel out. And again, I'm going to be left with the two letters on the very ends, and that's my answer, vector QP. Let's take a look at a slightly more challenging problem that's going to test our ability to conceptualize what we're reading. So we have Jiangsu, who is about to fire an arrow at a target. In normal, still conditions with no wind, she can shoot an arrow with a velocity of 18 meters per second. However, today there's a wind of 6 meters per second blowing directly across her path from the left. So we have two questions here. In which direction should she shoot the arrow so that it doesn't get blown off target and so that it hits the target? And what will its actual airspeed be after we've accounted for the wind? So the key to this problem is really setting up the correct diagram. Now, the first thing we want to draw is the wind vector. So we know we have wind blowing from the left, which means it's starting at the left and going to the right. We have a wind vector of 6 meters per second. Let's assume that the target, which is here, is straight in front of our shooter. This is the flight path that we want our arrow to take. But if she shoots the arrow directly along this path, the wind is going to push it over here and she'll miss the target. So she needs to adjust her aim. She needs to aim left a little bit. And we know that the arrow will travel 18 meters per second, but that is going to be affected by this vector up here. So notice how my right triangle, I know a couple things. I know the hypotenuse and I know the opposite side. And the first question I'm trying to answer is, what direction should she fire? Well, let's use this angle here, angle theta, to be our direction. And going back to chapter 10, we can solve for theta pretty quickly here. Theta is equal to the inverse tangent. We have opposite over sine here. So not the tangent. We have inverse sine of 6 over 18, or 1/3. And that is approximately 19.47 degrees. So the direction here, because we weren't giving any bearings, really we need to qualify our answer here. She should shoot about 19.5 degrees to her left. I can't be more precise with that in terms of bearings because I wasn't given any bearings in the problem. Now the next question is, what velocity or what actual speed will that arrow be traveling? And so to do this, I need to use Pythagorean theorem. We know that 18 squared, or the hypotenuse, equals my two legs, the sum of the squares of my two legs. So 6 squared plus x squared equals 18 squared. So to find x squared, I simply subtract 6 squared on both sides of the equation. Do a little bit of calculating. Square root both sides here. And I get x is equal to about 17 meters per second. And so this is my actual velocity. We need to be really careful here because most people, a lot of errors occur because people add these two numbers together. When you're given the hypotenuse and one of the sides, we need to use subtraction.